Hi, my name is Joe Kramer, and this is a quick tour of the energy grid calculator, which is a computational model students use at the end of OpenSciEd High School Physics Unit 1 about energy flow from Earth's systems. So this design project that students take on ties together everything that they've learned about electricity and energy and maybe most importantly decision making through the context that is grounded in the Texas power crisis of 2021. So the unit starts with students learning about what happened in Texas in 2021 and where people spent days in freezing weather, many without power. And they ask, like, why did this happen and could it happen here? Which drives the unit-long investigation into how energy is generated and transferred and delivered to their homes. So by the end, students are engaged in a design project where they are making changes to the energy system to make it more reliable for their own community. So to begin that process, the design project, so this is at the very end of the unit, students interview someone that they know in order to identify in their small groups criteria that matter to them and their families. So cost, reliability, environmental impact like carbon emissions. They rank those criteria to choose what their group is going to prioritize, and then they use those criteria to guide their redesign. So this is the energy grid calculator, which simulates an electricity system. This version is built for Denver, Colorado, but you can easily adapt it to other regions. And you can make a copy of this tool right now by going to bit.ly/denver-grid and just make a copy of this exact spreadsheet that you see in front of you. At the top, you'll see these performance metrics, production in comparison to the demand of the system and how much of it is coming from wind and solar. Currently, this is showing us statistics for our current grid. And we can see like roughly 4,300 kilograms per year of carbon emitted by the system, 2 measures of land use, and these measures of reliability. So the students can easily use these metrics to judge whether their current design or their redesign meets the criteria that they care most about. So on these solution tabs, students can make modifications. So if we scroll down, we can see that current grid and we can demolish power plants and create new ones above. So for example, they might choose to remove all sources or all fossil fuel systems from this from the grid, from the production capacity, in order to cut emissions. But they will immediately see how this tanks the reliability of the system as a whole. The system cannot meet the demand without replacing those coal plants and natural gas plants with other solutions. So then they try to fix it. They could add a nuclear power plant. And that does meet more of the demand, but it doesn't quite get there. So maybe they come to the realization, okay, we will add some of that natural gas production back, or even more of it. So that's still not getting us to 100% or even 90% on this reliability measure, but it has reduced carbon emissions significantly. Maybe they choose to include solar as a part of their solution. So maybe on 200,000 rooftops, we're adding solar arrays, and maybe they add 2,000 megawatt solar farms. We're still not to where we need to be. So maybe we need a second nuclear power plant, or maybe we need even more natural gas. So students are confronting the impact of the decisions that they're making using the measures shown by the energy grid calculator. Notice this measure of reliability that says for how many hours will all people have power if wind and solar drop to zero is still red. If we're relying on solar power, that solar is going to go away at night, and that demand is not going to be met. So they had to think about battery storage in order to solve this problem. A few lessons prior, they've done some research into what storage options exist, and they've modeled out using these energy transfer diagrams how this battery system works. So if we split the power coming from a solar cell, some of it's going to the system and some of it's going to battery storage, then we can deliver that battery storage at night to meet some of the demand. We can add that in the energy grid calculator as well. So for example, if we use 300 of these batteries, then we can start to meet the demand for a longer period of time at night. These batteries aren't cheap. We've actually made the system significantly more expensive, but we have cut the carbon emissions. So the heart of the challenge is in making trade-offs between these priorities, just like engineers and policymakers do. So this tool is built into a Google spreadsheet, so everything is editable. On this background this background data tab, you will see details on how you can localize it. So we can change details about the population of Denver or the population of the state. The spreadsheet is very, very complex, but all of that complexity is under the hood. So students can approach it quite easily to make the changes that they want to make. If you want to get deep into the weeds, you can even go down to some of the peer-reviewed sources that we're using, and you can change things like solar irradiance. Notice actually this number 3 is not correct for Colorado. It looks like it would be correct for like some area in Canada. So if we use a value that's closer to what it would be in Denver, like 5, that makes our solar much more effective. So we can actually use less solar and still meet our demand. So again, tweaking these numbers is a way of empowering students to test real-world solutions using a model that changes in real time in order to make informed decisions about the kind of energy system they want to live in. So it's not just about physics content, it's about applying that content in ways that matter and dealing with real-world solutions on a level that's still age appropriate.